Hello, everyone. Welcome again to the last part of that 8-hour Q&A that I've been doing. If you guys aren't familiar with what I've been doing, we reached 10,000 subscribers, and my way of giving back and saying thank you to you guys was basically giving back to you guys and doing an 8-hour part series of this. So this is the last part of it. All right, so I want to welcome, I see a lot of familiar names and a lot of familiar people like Savin, Donna, and Olivia. I want to welcome you guys as well as BM Tech. So welcome. Hello, everybody. Let's start off with our first question. And I believe the first question is incomplete. Savin, if you have the rest of, I think your question cut off, let me know what the rest of your question is, just because I believe temperature was needed to finish the question, since we would use the ideal gas law. So if you're here, Savin, let me know what the rest of your question is. But for now, I'm going to move on to Donna's question, and I'll get back to you once you put the rest of it up. Okay, so Donna asks, the heat of combustion of ethanol is, the heat of combustion of ethanol is 3, let me go ahead and start writing all the stuff that they give us down. 326.7. Okay. And this is our heat of combustion. And then next, we're also given 2-methylpentane is, okay, I'm just trying to see what we're going to do after. You're also given this amount, and then per mole. And then that's also, I believe, it is heat of our combustion, or enthalpy. How much energy is released during the complete combustion of 301 grams of 2-methylpentane? Okay, so the heat of combustion of our ethanol is that. We're given 2-methylpentane is that amount. How much energy is released? And there's a part 2 to this question. Okay. Let's see what I can do with that. So I have to convert my grams to moles of 2-methylpentane first. So I have to figure out what the molar mass would be for 2-methylpentane. So let's start there. Let me write out what that would have been and how I would figure that out. Methylpentane. And then what I'm going to do is pretty much just draw it out for right now. And then I'm going to translate that and see how many of each, like carbons or hydrogens, there are, and then figure out the molar mass of it. So if I were to draw this, I would start this off with pent. So pentane, it would give us 5 different carbons. So I'm going to draw this out, 1, 2, 3, 4, which really I drew 5 carbons. And then next I would put a methyl on 2. Okay, then next, I'm just going to count how many carbons we would have. So here we'd have 1, 2, 3, 4, 5, and 6. So there are 6 carbons, and I'm going to count how many hydrogens we have. So on this end, there would have been 3. Here, there would have been just 1. And then here, we also would have had 3, 2, 2, and 3. So we'll add all those together. So 3, 3, and 3 would give us 9. That would give us 10. In total, we would get 14. Okay, so far, that's what 2-methylpentane would look like. And then I'm going to figure out what the molar mass is to convert that to moles, and then later get the entire energy. All right, so let's figure out the molar mass. So carbon is 12.01. Multiply that by the 6 subscript, and we'll see what that gives us for this. So then that would have been 72.06. And then for hydrogen, this is really 1.01 times 14. And then I'll add those 2 values together. Okay, here, let me add these up. So I'm adding these 2 values together to figure out what the molar mass is. And this gives us 86.2 grams per mole of 2-methylpentane. So now what I want to do is I'm going to bring back that 301 grams. And then and this is of the same exact compound here. So then I'm going to multiply this by the molar mass, but really leaving 1 mole on top. And then on the bottom would have been that 86.2 grams. And that's going to cancel out the grams and the grams. And then next we would go on to figuring out what our energy is. So the fact that they gave us, let's see, the heat of combustion of ethanol. They also told us the heat of combustion of 2-methylpentane. I would focus on just the heat of combustion of the 2-methylpentane right now, since that's I mean, essentially what we're looking for, right? So I'd multiply this by, I'm going to use this as a conversion factor. Here we go. I'm going to use this as a conversion factor. And then next, what I also want to look at is, because they're telling me ethanol, let me see if I would need a balanced equation, which I believe we do need a balanced equation, just to see how many moles there are, and the fact that they give us ethanol. So let me see real quick what that would give us. And then here, because ethanol would have been this. H14 plus ethanol CH3OH. And then we can figure, I believe everything's going to be 1-to-1 regardless. But let's see what I can find just to quickly balance this out. But hold on, but it's saying combustion. So let me just make sure I have my balanced equation, because it is saying combustion. Ethanol, the heat of combustion of ethanol is that, while we're given that amount. I'm just going to go with it. So this would have just been, because they're just telling us it's 1 mole of that. Yeah, I think I'm overthinking it. And then 993, there we go. That's it. That's all you would essentially do. Now, the fact that they're giving you the heat of combustion of ethanol, I don't see why they're doing that, unless I think it's part of the second part. It is part of the second part. Okay, yeah, it's part of the second part. Then for this part, I would have just multiplied and then divided. So here, this is the setup for part 1, and then I'll use the other information for part 2. So here, 93 divided by 86.2. And then this would have given us 3,467 kilocalories. And then they're telling us energy is released. So the fact that it tells us it's released, it's negative. So I know our actual energy would have been negative. So this would have been the first answer for part 1. And then for part 2, I'm going to do pretty much the same exact thing. Instead, I'm going to use the enthalpy that they gave us before, or the heat of combustion, same thing. And then here, this is still going to be, they don't give me a unit, so I'm going to assume it's just kilocalories per mole. And then for ethanol, we're pretty much going to approach this the same exact way. Since part 2, they're stating, you find it part 2, assuming the same efficiency, would 301 grams of ethanol provide more or less, or the same amount of energy. So we have to figure that out once again. So what we have to do is use, hold on, it's ethanol, not methanol. That's methanol. Ethanol would have been this, so that's not it. Ethanol has 2 carbons, so I would have done 3CH2OH. Okay, so that would be ethanol. And then now I have to figure out the molar mass of that as well, and then multiply and pretty much do the same process. So let's see if it gives us the same value. So we have 2 carbons, so C is equal to 12.01 times 2. And then how many hydrogens do we have? We have a total of 3 plus 2, 5, and then 6. So 1.01 times 6. And then oxygen is just 16. I'm going to add up all of those values. This would have been 24.02 and 6.06 and then 16. So let's add up everything to figure out the molar mass. And let's see what this gives us. So this gives us, and multiply this by the 46.08, technically dividing, and then giving us 1 mole. And this is still of ethanol. Now, next I'm going to use the heat of combustion for ethanol that they provided. So I'll put that on top since that's what we're looking for. And then on the bottom, I'll put the moles so they can cancel. And then multiply and divide, and that would give us our answer. So let's see what if it's the same or if it's less. Okay, it's actually going to be less. So 2,134 kilocalories. And is it telling you if it's also being released? Assuming the same efficiency, then yes, I would assume that it's still being released. So it would have been negative. This would have given you actually technically more since it's negative, right? It would technically give you more because it's a negative. it's a little bit higher than this negative 3,467. Cool. So that's what your answer would have been for that one. And then Donna, I know you asked, will you be posting videos on organic chemistry in the future? Yes, I do plan on doing organic chemistry in the future. I don't know the exact timeline of it just yet, but I definitely will be doing OChem first part and the second part. But right now I'm trying to finish up general chemistry, the first half and the second half. And then I will be slowly adding some OChem. But you're always welcome to still ask on the Sunday sessions or Q&As, OChem questions. Let's see who's next. Okay. All right. So Olivia. All right. So Olivia asked, how much heat needs to be absorbed? So I know so far heat is going to be positive because it said it's absorbed. And then it gives us a mass. So 100 grams of H2O of water. And then we're also given it's at 5 degrees Celsius. So our initial temperature is 5 degrees Celsius. And I believe they're telling us our final temperature, which is 75 degrees Celsius. And then this is of water. So the missing information here that they expect you to know is your specific heat capacity, which for water, it's always going to be 4.184 joules per grams divided by Celsius. So in this case, what we're going to use is this formula, as some may call it MCAT to remember it, but this helps us figure out how much heat is either absorbed or released. So all we have to do is pretty much plug everything in. Everything is in the correct units because we actually want temperature to be in Celsius and we want our mass to be in grams. So plug everything in and that'll give us our answer. So this would have been 0 grams. And then the missing part, I believe, that maybe, made it tricky was just knowing what formula to use as well as this essential information. Okay, so definitely know that for your exam. Sometimes they won't give that to you. And then your change in temperature is always going to be final temperature minus the initial temperature. And that's what I'll do here. So our final is 75 degrees Celsius minus the 5. And then that would have been really 70. So I'll multiply all these values together. And then that'll give us our heat. So 100 times 4.184 times 70. Oh, let me do that again. Okay. This gives us a very large value. So 29288 joules. You'll see that Celsius cancels. Same with the grams. And we're just left with joules. Sometimes they ask you to convert into kilojoules if it's such a large answer. Depends on what your teacher wants. But in this case, I can show you both. I would multiply this, and then this would be 1 kilojoule, and then on the bottom, 1,000 joules. And then in this case, I would really just move the decimal place over. So this would have been here. This would have been 1, 2, 3. And then it would have been 29.288 kilojoules. Okay. That would be our overall heat that's absorbed. Okay. And we'll just keep going down the line. Then you said my other question is here. Okay. My other question, the reaction below has a 96.8% yield. And then, by the way, guys, if you have multiple questions, that's totally fine right now. We do have until 1 o'clock. So I'm just going to be going in order. So if you have multiple questions, by all means, ask them. That's totally fine. We have plenty of time. Okay. So 96.8% yield. And how many actual grams of calcium sulfate are recovered when 5.24 grams of SO2 reacts with, and then they give us our balanced equation. So let me write that out. So 2 here, just writing out the balanced equation that you provided. O2, and this gives us 2 calcium SO4 plus 2 CO2. Okay, so I'm looking for the actual yield. And let me just go back to the question. So I'm given the percent yield, how many actual grams, thank you, that's what I need. How many actual grams of this product did we produce? So the missing information that we need right now is the theoretical yield. And how I can tell that already is due to the formula of percent yield. So percent yield is going to equal our actual yield, which is what we're solving for. And then actual yield is really just of that product, which in this case, they're asking for calcium sulfate. And then on the bottom would have been our theoretical. Okay, so our theoretical yield times 100 since it is a percentage. So what we're missing, because we're given our percent yield, right? We're given this, we're looking for our actual yield. We have to figure out what our theoretical yield is. So what happens is that for your theoretical yield, you're going to find that using stoichiometry. Now, they gave us some sort of amount of our limiting reactant. I know they don't state the limiting reactant, but by the fact that that's the only thing that they gave us or provided, then I know that SO2 must have been the limiting reactant. Therefore, whatever the limiting reactant produces is your theoretical yield. So that's what we want to do now. What we're going to do, what the plan is to go from grams of SO2 and then eventually make our way to grams of calcium sulfate, which is our product. For limiting reactant questions or anything involving theoretical yield, you go from the grams of your reactant to the grams of your product. So here I'm going to go from the grams of SO2 to the moles of SO2, then do a mole to mole ratio to get a different compound or the compound that we want, which is our product of calcium sulfate, and lastly get to grams of calcium sulfate. So what I need now is the molar mass of SO2. So let's do that separately. So figuring out the molar mass of SO2, sulfur is 32.06, and then oxygen is 16 times that 2 subscript, giving us 32. We'd add these two together, and that would be 64.06 grams per mole. And then what I'm going to do is I'm going to align the units across so they can cancel. So the 64 always goes with the grams, or whatever molar mass we get always goes with the grams, and it's always per 1 mole. This is still of SO2. Your grams and grams of SO2 would cancel. Now we're left with moles of SO2. So I'm going to convert that to moles of what we're looking for, which is calcium sulfate. So moles of calcium sulfate would go on top, moles of SO2 on the bottom, so those can cancel. And where I'm going to get this mole to mole ratio is from the balanced equation. So you'll note that they gave you 2 moles of SO2 for every 2 moles of calcium sulfate. So that's exactly what I'm going to put here. So 2 and 2. And then next, since those two canceled, now I'm going to get to grams of our product, which is calcium sulfate. So separately, we need to figure out what that molar mass would be. So I'll do that. So calcium sulfate, let's figure out what that molar mass would look like. So calcium is roughly 40.08. Sulfur, we said, was 32.06. Oxygen was 16 times that 4 subscript, giving us 64. We'll add all of these up, and let's see what that gives us. So 40.08 plus 32.06 plus 64. Okay, that would give us 136.14 grams per mole, and that's what I'm going to put on top. So I'll put the molar mass that we just found, and then we'll multiply everything out, and that would give you your theoretical yield, and then we'll keep going. So let's multiply everything out. So I'm going to multiply the 5.24 times the 2 times this value, and then divided by these two, and then we'll see what that gives us. So 5.24 times everything on top and divided by everything on bottom. And here. This would give us 11.14 grams of calcium sulfate. So this is our theoretical. I'm going to go back to the percent yield formula, and we'll see what this gives us. So percent yield, right? Percent yield is equal to the actual yield divided by the theoretical times 100. How I remember this is percent yield is where it's at, right? So there, that's just something to help me remember which one goes on top, which one goes on bottom. And then now I'm just going to start plugging in all the values that we now know. So we know our percent yield since that was provided, the 96.8%. And then actual is what we're solving for, so I'm going to state that's x. And then our theoretical was what we just found, which is 11.14. And then I'll multiply that by 100. Now, I'm actually not going to multiply by the 100. Instead, what I want to do is divide both sides by 100 to get rid of it. And then to get rid of that percentage and put it into pretty much just a regular number. So it's no longer going to be a percentage. I would move this decimal place over twice to the left. This would give us 0.968, cancels out the 100. And then now my last step is to multiply both sides by that 11.14. And then let's see what that would give us. And that would give us our actual yield. So x is equal to, let's see what that is. So 11.14 times 0.968. This would be 10.8 grams of calcium sulfate. That is our actual yield. Okay, that's how you would do that. Let's see who's next. Okay. Dev asks, can you do a problem on titration? Sure. So I can keep it kind of here. Let me pull up an example. There's a lot of different things I can talk about titration, but the most common ones that I typically see are finding the equivalence point. So that's what I'm going to do. And let me pull up an example of pretty much how to figure out the equivalence point. But let me grab an example for you with that here. Let me see where I have that. Just going to pull up how to figure out the equivalence point for you. But let's see. Sorry, just trying to figure out one. Here it is. Looking for examples. Yeah, if you guys have specific examples, that helps me a lot because it helps me know what you're struggling with. So rather than just general topics, it just helps me actually answer your question since I can go on and on about pretty much anything on chemistry. All right, let's say if we were asked to find for this question, find the volume of really, I mean equivalence point. Okay, equivalence point of, let's say, of HCl. Find the volume of HCl given, actually, let me give you the concentration. Let's say if they actually gave us of 0.100, find the volume of, okay, molarity of HCl with 40 milliliters of 0.200 molarity of KOH. Okay, let's say something like that. So this is how to figure out what your equivalence point is. The first thing that I would do with these types of questions is just write out the balanced equation. So what you're always going to see with these types of titration questions, essentially, it's really just an acid-base neutralization reaction. And what that entails is we have our acid, we're going to add base, and what that's going to form is a salt and water. Okay, so in this case, our acid would have been anything that begins with H, so that's HCl. Our base would have been anything that ends in OH, so KOH. And then what would form is our salt, so you'll note that this K and Cl would join together and form our salt, so KCl. And then OH and H would form H2O. Okay, so that's what that would have been. It is balanced. I chose a nice one. It would have been balanced, but for some that are not balanced, like let's say like if it were H2SO4, this is known as a diprotic acid, or anything that has like 3 hydrogens, that would have been known as a triprotic or polyprotic acid. Those are not going to be balanced, so make sure to balance those types out. All right, so then what I'm going to do now, let's figure out what we got, what we have, what we're given, and then what we're trying to find here. So now that we have our balanced equation, we have 40 milliliters of KOH. We also have the molarity of KOH. And then molarity is going to be used as a conversion factor. So what I like to do whenever I see molarity with these types of questions is automatically break it apart. So molarity is really just moles divided by liters. So think of molarity as moles divided by liters. And how I'm going to rewrite this, it's really 0.2 moles of KOH divided by 1 liter of KOH, okay? So that's how I'm going to break it apart. And then next, we also are given our molarity, which I'll break apart as well, of HCl. So molarity, this is really moles over 1 liter of HCl, okay? And then now what we're asked to find is just the volume, so milliliters of our HCl. So what helps me start, and I know it's going to be like strange when I first say it, but what has always helped me with these types of questions is whatever you're finding, that HCl, where you're going to start is whatever you're not looking for. So since I'm looking for HCl, but I'm not looking for KOH, I'm actually going to start with KOH. So you start with the one you're not looking for. That's just always going to work, okay? So in this case, I'm going to start off with the 40 milliliters of KOH. And then my plan here, let's go ahead and go over the plan because this is a little bit of a longer process. So our plan here is to go from the milliliters of KOH. We're going to change that to liters of KOH. Then using the molarity, we'll get to moles of KOH. Now that we got to moles, we can do a mole to mole ratio using our balanced equation and change this to moles of what we're looking for, so HCl. Then lastly, using the molarity that was provided of HCl, I would change this to liters of HCl and then convert it back down to milliliters of HCl. Okay, so that's the whole process. That's what we're going to do. So then I'm going to start off with the 40 milliliters of KOH, convert that to liters, so 1,000 milliliters on the bottom of KOH so they can cancel per 1 liter of KOH on top. And then next, so milliliters would cancel. I'm going to use the molarity that was provided right here. So 0.2 moles of KOH on the top per 1 liter of KOH on the bottom. Liters and liters would cancel. Now we're at moles. So I want to put the moles of KOH on the bottom and moles of what we're looking for, which is HCl, on top. Where I'm going to use this, where I'm going to find this, is the balanced equation. So everything, you'll know everything is just a 1 coefficient since it's completely balanced. So I would look and see, oh, there's 1 mole of KOH per every 1 mole of HCl. So then I'll put a 1-to-1 mole to mole ratio. And then next, our moles of KOH would cancel, and we have our moles of HCl. Now we want to use the molarity that was provided, but this time we're going to flip it. So our moles of HCl would be on the bottom per every 1 liter of HCl. The molarity that was given to us was this one. Okay, so this one. So I'm going to use 0.1 moles on the bottom. So 0.1, and then I'll multiply this by 1,000 since I want to change this to milliliters. So multiplying this by 1,000 milliliters per every 1 liter of HCl, and then that would give us our answer. Okay, so then now I'm just going to multiply everything out, and what I'm multiplying is this, 40. So I'm going to multiply the 40 times the 0.2 times 1,000 and divide it by 1,000 times 0.1, which automatically I could actually cancel out these thousands, and then it's a little bit simpler. So let's multiply everything and divide and see what we get. And this is once again finding our equivalence point or just finding the volume needed to neutralize this solution, okay, or this reaction. So we would have gotten 80 milliliters of HCl. That would have been our final answer. Now, if you need some more help with these types of questions, it's called solution stoichiometry for those of you who aren't familiar with titrations. I do have a video on it. I believe it should be titled Solution Stoichiometry or Molarity. I'll put a link in the chat right now to that video. There's actually even a practice problem in the description box that you can try out as well. And in the video, there's also another problem that I actually have two examples, come to think of it. Yeah, I have molarity, solution stoichiometry, one video, and another one on solution stoichiometry. So definitely check those out. There's even one part of the question that's the dilution problem. So this is really, really helpful. Make sure to check those out. And I'm going to move on to the next question. Okay. Let's see. All right, Victoria, you ask, and let me make some room. All right, let's see what your question is. Aluminum has a specific heat of, so automatically we have the specific heat of aluminum. So this is 0.9 joules per grams Celsius, and this is 0. How much energy, so we're looking for Q, or really heat, is needed to, is needed to raise the temperature of, so we're given a mass of aluminum, 625 grams, and we're given our change in temperature. So T initial, or our initial temperature, is 37.7 degrees Celsius, or 30.7 degrees Celsius, and our final temperature is 82.1 degrees Celsius. And then this is the formula that we're going to use. So in this case, we're using Q is equal to, some people call it MCAT. This is one to definitely know. And all I'm going to do is pretty much plug everything in. The main thing that I need to focus on, though, is figuring out our change in temperature. So our change in temperature, and that's what this little delta symbol or triangle means. It just means change, where I'm going to subtract our final temperature minus the initial temperature. And then I'm going to expand this formula a little bit further. So instead of just this change in temperature, I'm actually going to expand it to just be T final minus T initial while this loads. Okay, so that's what I was going to do. I'm really just going to plug everything in. And I think it's just understanding what the formula, like what everything in our formula is. Come on. All right, while this loads, give it a second. It sometimes does that after I'm working so much on it. There we go. Okay. So I'm just going to plug everything in, but I'm going to change this to T final minus T initial. Plug in everything that we're given. So we're given our mass, our specific heat, which is C, so 0.900 joules per gram Celsius. And then we're also given our final and initial temperatures, so 82.1 Celsius minus that 30.7 degrees Celsius. Okay, so I'm going to do this all. I'm going to start off with what's in parentheses. So 82.1 minus 30.7. This would have given us 51.4 degrees Celsius. And you'll note that your Celsius and Celsius would cancel, same with your grams, and you're going to be left with joules. And at the end, we will convert this to kilojoules since that's what the question asked for. So I'll multiply everything together. And this gives us very large number, okay, in joules. Now we'll convert this to kilojoules. So converting this to kilojoules, here, let me rewrite this. I'm going to divide by 1,000 joules, and that would give me kilojoules. So really what I'm doing, this is a J. I'm going to move this decimal place over 3 times, 1, 2, 3, and this is really 28.9125 kilojoules, and I can round. So looking at our sig figs, let's see how many sig figs were, like the lowest amount that were provided in this question. It was 3. So I would round to 3 sig figs and stop at that 9. So really 28.9 kilojoules would have been our answer. Okay. And let's move on to the next question. Okay. Oh, it's a two-part. Okay. How the pH of any salt, acid, alkali is analyzed experimentally or theoretically. What is pH? Okay. So let's see. I'm going to start off with what the pH is, what we're all kind of like looking at when we're looking at salts and acids. So what pH is really referring to, it's the measure of our concentration of our acid. So like this would have been the formula, by the way. You could have seen it this way. You could have also seen it as your hydronium ion, which is this one that I'm writing. But really what pH is measuring is how much acid is within your mixture or within your solution. Okay, so how acidic or basic your solution could be. Now, that's referring to something that's when you're asking how the pH of any salt, acid, alkali is analyzed. So experimentally, what we could do was there's several ways, but two main ways that you would see is you would use pH paper or litmus paper that you literally would dip it into the solution, and if it turns blue, it's basic. If it turns red, it's acidic. So that's one way to experimentally test if there's like what your pH would be. And then like using, there's, I believe, a little chart on the actual like litmus paper, like bottle that you can compare whatever color it would be, and you would pretty much like estimate what your pH would have been. So that's one method. The more specific method and more exact method would be using an actual pH electrode, where you would get your solution and you would put your electrode in your solution, and then it would actually read and tell you exactly what the pH is. So those are two different ways that experimentally you would actually do any of these types of reactions to figure out, what the pH would be. Theoretically, what you would do is use this formula that I just wrote down. So theoretically, what you would do is you would figure out how much concentration of your acid that you have, and pretty much just plug it into this formula. Take the negative log of, let's say our concentration was 0.30 molarity of our acid, and you would actually plug in that value. And so negative log of this concentration, and then that would give you your actual pH. And let's see what that would have given you, and then you can figure out whether it's basic or acidic. So 0.52, then that would have been very, very acidic, right? Anything that is below 7 is acidic. Anything that's above 7 is basic, and 7 is neutral. So I believe that was your question, but that's really what you would do experimentally or theoretically. Let me know if that was enough to answer your question, but I believe that's what you were asking. Okay. All right, let's move on to the next question. All right, Liz asks, can you go over mole ratios? Sure. So let's say I want to pull up an example real quick of multiple ratios. I just want a balanced equation. Cool, found one. 2NO2Cl and 2NO plus Cl2. Okay, let's say if we had some sort of balanced equation here, and if we were first given you have 3.7 moles of NO2Cl, find the moles of Cl2. Okay, so if you were given something like this, what I would start off doing is starting off with your given, since that's the only value that you're provided. And then whenever you're trying to change the compound altogether, which is what we're trying to do here, because the question asked us to go from this compound to a completely different one. Well, that's how you know you're going to use a multiple ratio. And where you're going to get that, like those numbers from, is from your balanced equation. So in this case, our balanced equation gives us 2 moles of NO2. And then I know it doesn't state it here, but since there's no number in front, we can assume there's actually a 1 in front of that Cl2. So this is our other mole-to-mole ratio. So our mole-to-mole ratio would be set up this way, where I would multiply, and what I want to put on the bottom, and what you always want to do here, is align the units so they can cancel, and then on top put the unit or put whatever you're trying to solve for, whatever you're trying to get to. So Cl2. And then now where I'm going to get these numbers, once again, is from our balanced equation. So there's 2 moles of NaCl per every, and this was a 1, so this was a 1 mole of Cl2, and then I would just divide, and that would give us our answer. So 3.7 divided by 2, that would have been 1.85 moles of Cl2, which I would round up since our answer, or our value, was just 2 sig figs, so 1.9 moles of Cl2. So that's how you would use a mole-to-mole ratio. I do have several other examples. I have a video on mole-to-mole ratios that I can put in the chat right now to help you better understand it, but that's really the main concept of it, is using, like, where we get that from is using the balanced equation, okay? The numbers in front of the compounds or whatever we're finding, okay? So yeah, I'll put that in the chat. So it's mole-to-mole ratios is the title of the video, and yeah, I hope that makes some more sense. And definitely check out that video here, because that'll help even more. Let's see who's next. Okay. I think I'm going to need another formula for this. So let me look at my formulas, because I have a feeling what's coming. I think it's that one. Okay. Let's see. Yes, it is. Okay. A hydrogen atom absorbs a photon of visible light, and its electrons move from n equals 2 to n equals 4. So the fact that they gave me that already is this must have been our initial and our final. So cool, that would have been that. Now, where am I? Calculate the wavelength. Okay, in nanometers of the photon. Got it. So I'm looking for wavelength, specifically in nanometers. The formula that I want to use that would allow me, the formula that I would use that would allow me to figure this out. By the way, guys, so the formula that I'm about to use is also in my formula sheet. I put it in my chemistry, chemistry survival guide. So I just put that link right now. If you want to download that, it's completely for free. That's really going to help you out if you haven't downloaded that already. It's all the different formulas that you will possibly need or see, all laid out pretty much in one document, so you don't have to go searching through your notes. Same with all the different polyatomic ions. I put those there. Same goes with like the geometry of Lewis structures. A lot of helpful things, oxidation numbers that you need to know. Okay, make sure to check that out. So continuing with this question, our formula that we would use would be this one. This is 1 divided by our wavelength, and that's going to equal this constant. Okay, this is in meters to the negative first, divided by Planck's constant times our speed of light. And then times 1 divided by n initial squared minus 1 n final squared. And I'm now going to plug in all the values. Now, h and c are just constants that are known. So h is called Planck's constant. That's 6.626 times 10 to the negative 34th joules times seconds, and the speed of light is 3.0 times 10 to the 8th meters per second. I've also seen it as 2.998 times 10 to the 8th meters per second. It doesn't matter which one you choose. So now I'm going to plug everything in, and we're looking for a wavelength. Okay, so plugging all of our values in, let's see what we get. So I'm just going to set this up for you guys. So this is times Planck's constant. Okay, joules times seconds. I'm going to multiply that by the speed of light. All right, and then now I'm going to bring in the n that was provided. Okay, so this is really just the energy level that the the electrons going up to. So this would have been Ni, or the initial would have been 2 squared minus 1 over 4 squared. And then what I'm going to do first is I'm going to do what's in parentheses. So I'll square these values, and figure out what that is. So this would have been 1/4 minus 1/16. And I'll separately do that on my calculator. So 1/4 divided, or actually minus 1 divided by 16. So this would give us 0.1875. And then now I'm going to figure out what all this is. Okay, so let's see what that would give us. I'm going to do the bottom first, just so separately. I like to kind of separate everything on my calculator so I don't make any calculation or calculator mistakes. All right, and then so this is what the bottom is. And then I would have this same thing on top. Okay, so let's see what that is. 1.09737 to the 7th power. Yep. Okay, so I would have gotten 5.52 times 10 to the 31st. I'm going to multiply those two values, and then I'm almost done. All right, this is still going to be 1 over wavelength is equal to 1.035. This would have been in meters. Now, how I know that is by going back to the units. Here we would have seen that, let's see, seconds and seconds would cancel. And actually, this would have been given in joules. But there was that would have canceled. It would have given you meters. It has to give you meters regardless for your wavelength. Okay, so don't worry too much about that, but that's what it would have given you. And then I'm almost done. All I have to do is pretty much flip this. So what I'm going to do is take the reciprocal of this. Okay, this is a negative first. Take the reciprocal of this, and essentially what's going to happen is it's just going to give me my wavelength. So now this is 1 over 1.035 meters. And then now let's see what that would have given us. So wavelength is this, 0.966 meters. I'll convert that to nanometers. And then times, this would have been 10 to the negative 9th meters per every 1 nanometer. So I'll divide that, and let's see what that gives us. So it's going to give you a very large value. Okay, nanometers, and that would have been it. What you could have done is just written this in scientific notation, which I do recommend, which would have really been 1, 2, 3, 4, 5, 6, 7, 8. So 9.6 times 10 to the 8th nanometers. That's what I would say to leave it as. Okay, it was just knowing that formula. All right, let's see what else. Okay, let me make some room. Alrighty. Okay, so Breck says, can you talk about redox? And we have our example. How would I know when an equation is reduction or oxidation? So in a redox reaction, it has to have both oxidation and reduction. So I'll go over how to find that. Just to let you know, like redox, and it's in the name. Okay, redox is in the name, where you would have reduction and you would also have oxidation. Okay, so you have to have both for it to be so both of these have to be within the same reaction for it to even be a redox reaction. So I'll show you how to figure out which one's which. All right, so our formula was, or our balanced equation was given as this. Okay, this is plus silver going to copper 2 plus. And this is aqueous plus 2 silver solid. Okay, so first things first, we have to figure out our oxidation numbers, and I'll figure that out. Looking at copper, whenever something is on its own or by itself, like copper, like one element on its own, that means it's going to have an oxidation number of 0. So this is 0. Okay, and this has an oxidation number of 0. Next, anything with a charge has the oxidation number of its charge. So plus 1 would have been this oxidation number. Same goes for copper 2+. Our charge is really our oxidation number. And then next, once again, anything in like that's by itself. So silver, it's on its own, it's by itself. That has an oxidation number of 0. This 2 doesn't mean that it's, there's 2 of them. It really just talks about the balanced equation. We're not looking at that specifically. Now, what I'm going to look at now is our change in oxidation numbers. So I like to compare, we look at the reactant going to the product and see what happened, what changed. So going from copper 0, right, it has an oxidation number of 0, going to 2, it just increased. Whenever we're becoming more positive, that's oxidation. And the reason why oxidation is actually a loss of electrons, remember electrons are negatively charged. So we become more positive as we lose more negative things, right? So that's kind of how I think of oxidation. Just look at it as it's becoming, our oxidation numbers are becoming more positive as we go from reactants to products. And reduction is the opposite, where if I were to look at silver, we're going from +1 to 0, so we're reducing, so that becomes more negative, which is reduction. Now reduction is actually gaining electrons. That's why it's becoming more negative, since electrons are negatively charged. So that's what we would look at. That's how you would know which one's which. Okay, so hope that makes similar sense. I also have a video on redox reactions, so you can try out another one. Yeah, I'll put that in the script in the chat right now. It also goes over, what else? It goes over reducing agents and oxidizing agents, and which compound or element is being oxidized or reduced. So I also cover that as well. Those are common test questions, okay? So I'll put that in the chat. I also have, by the way, guys, I also have notes that I make. Think of it as like how-to guides, and they are extremely helpful. I've heard a lot of students tell me how like this basically moved them up from a C to a B or a B to an A. Think of it as it's pretty much it's everything that you possibly need to know about, let's say, redox reactions. I've included how to balance them under acidic conditions, several different ways to figure out oxidation numbers, so many examples. I just put that in the description, in the chat. So make sure to check that out. You guys could even see what it looks like by clicking the link, and then you can kind of like get a glimpse as to how much is actually in there. Yeah, you're welcome. And then, and I know we went over titrations and molarity, so I'll also put the notes for that. I have so many different ways to figure out, like doing molarity problems, how to figure out the molarity, how to use it as a conversion factor. Same with solution stoichiometry, how to figure out the concentration, the volume, the list goes on. I put as much that I can possibly think of that they can throw that I've seen on exams in my notes. I always use previous test questions, okay? So let's see what our next question is. Can you go over naming acids? I am just confused on what the subscripts. So Freya is saying, can you go over naming acids? And then also, I'm just confused on what the subscripts G and Ag mean. Okay, real quick, I'm going to go over the G and Ag mean, what all of those mean. So what G means, it's gas. Okay, so this is how we would write it. And let's state with, you would have like N2 gas. Okay. G really just stands for, and I don't want to put an arrow, just stands for gas. So G means gas, while S means solid, while Ag means aqueous. So that's really what you would an L, there we go. L means liquid. That's all they're really talking about. And now in this case, AQ really means aqueous. Sorry about that. And what I'm saying is aqueous just refers to there being water in the solution. Okay, that's like, I know it's a fancy word for that, but really it's just saying that there's water in the solution. So that's what those mean. Hope that makes more sense. Let me go over naming acids. And let's see. All right, so naming acids, there's going to be two different types of acids that you would see, some that contain oxygen and others that do not. So our first type, the one that has no oxygen, oh, let me go back. There we go. No oxygen. How you can tell there's no oxygen, there's going to be a prefix that states hydro. So hydro isn't talking about hydrogen, it's actually giving you a hint and saying there's no oxygen involved. So let's say if you had something like hydro, and let's say you had, I'm going to say fluoro, so fluoric, and I swapped those. Let's swap these. There we go. Hydrofluoric acid. All right. So if we had something like this, the fact that they stated hydro tells us there's no oxygen whatsoever in this acid. And then now our acid portion is just going to tell us that there's a hydrogen there. Okay. Next, this fluoro. This portion tells us what element that is. So that sounds like fluorine. So just F, negative charge. We're still going to balance out our charges. So this is HF. That's hydrofluoric acid. Then next, if I were to have something that actually has oxygen, so I'm going to say, yep, has oxygen, then this would not have that hydro prefix. There's actually no prefix that it would have. Instead, you would have two different types of setups. So you would have like the root name of whatever element you have, like you could have like sulfuric, what else? You could have nitric and so on, phosphoric, and you're either going to end in ic or us, and that's acid. Now this goes back to having to know your polyatomic ions, where ic goes with 8 and us goes with ite. So let's say if I had something like sulfuric acid, that acid, once again, just tells us that there's an H in front. Now, this ending of ic tells us it's actually sulfate, right? Sulfate. And then remembering what sulfate is, that's SO4 with a 2- charge. And then, of course, we'll balance out our charges. So this 2 would go down. This would have been H2SO4. And then what if I were to instead get sulfur us acid, then that would have been sulfite because the us goes with ite. So that's really SO3, 2-. The acid tells us there's an H in front. Then that us tells us it's sulfite. So that's going to be SO3 with a 2- charge. I'll bring that 2 down, and that's what that would have been. And then that's really the main concept with this. It's just knowing the two different types, ones that contain oxygen and others that do not. So I have a video on naming acids if you'd like to practice, which I definitely recommend doing so. I'll put that video in the chat right now. I go over so many different examples in that, so make sure to check that out and try them on. I would actually even say pause the video and try them out on your own. That really helps you, know if you are understanding the concept. It's just practicing, so many times that you no longer get it wrong. So let's see our next question. All right. Okay. And hello, Esther. Welcome back. So your question is, if you reduce the volume of a contained gas by 1/2. Okay, so our volume of a contained gas by 1/2 while holding the temperature, what happens to the pressure? Okay, so by the fact that it's stating holding the temperature, that means temperature is constant. Okay, so temperature in this case is irrelevant. We're not going to use it. Instead, we want to compare the relationship between pressure and volume. And this goes back to Boyle's law, where Boyle's law states, like remember doing that P1, V1 is equal to P2, V2? Well, essentially the concept is as we increase one, the other one decreases. So this is really the only one that is inversely proportional to each other, while everything else is proportional to each other. So what I'm going to do, think of it this way, if they're saying us if we reduce our volume, that would mean that our pressure would then increase. So that's really the main thing with this, is just seeing what would happen to the pressure would increase. Now, if I wanted the exact value, I could figure that out by using this formula. Okay, and we can actually kind of like make up values, but really using here. And that's actually exactly what I'm going to do. I'm going to make up some values just so you can see what would exactly happen to the pressure. So besides it increasing, let's say if our pressure started off as 1 atmosphere, okay, and we wanted to figure out what that last part was. And then I'll state, let's say, since we're chopping this, in half. So we started off with a volume of 20 liters, and then we chopped that in half, so now it's 10 liters. If I were to plug this in, we can then figure out what happened to P2. So this would have been 1 atmosphere times 20 liters is equal to P2 times 10. Okay, so I would multiply, this would give us 20, and then atmospheres times liters, and then this would have been still the same. Now I'm going to divide by 10 liters, and this really just cancels out to 2. So P2 is equal to 2 atmospheres. So right then and there, you can tell if we chop the volume in half, we then double our pressure. Okay, that just goes back to the idea, as you decrease one, the other one increases. So inversely proportional to each other. But you could always check that whenever they give you like, oh, we chopped this in half, or we multiplied by 1/3 or something like that. You could actually pick values and then plug it in, and then that will give you the same answer for each. Okay, so that's something to check for. Okay, let me go back. Sorry, guys, I think we skipped a few questions. So let me go back to see what else we had. Someone said, this is so handy for a lot of people, but I got different math because I live in another region. Sorry to hear about that. Yeah. I'm going to go to Lizette's question here. Yeah, I know in other regions they have different ways of learning. This is just how I personally learned it. Let's see. So Lizette is saying, question, how to write chemical equations for the second ionization of lithium, effective nuclear charge for an ion, for example, O2 minus versus O neutral. Okay. Let's see. So let me look at my periodic table, but we're looking at, for the second ionization energy. Okay. Equation of that here. Let me see what I can do with that. But second ionization of it. Okay. That would mean it would go to 2 plus. Okay. I believe with that, since we're looking at second ionization energy, what that really is talking about is the amount of energy needed to remove an electron. So I would put the electron on the product side, but I'll show you what I'm doing there. Here, first what I have to do is figure out what the first ionization energy is, and then I have to figure out the second ionization energy. So what I'll start with is just our lithium in its solid state. So I'm just taking this from, what does lithium typically prefer to be in its like ground state or regular state. So that would have been in its solid state. And then next we want to have this be some sort of charge now. So now this is lithium plus, and then what I would do is I would just add an electron on the opposite side. The reason why I'm adding an electron on the product side is because our electrons or our charges have to be the same. And if this is a +1 and this is a -1, then those cancel out to give us 0, which would mean that, yes, it works because now it's neutral. So this is just our first, I'm going to say IE1. That just means our first ionization energy. And then I'm going to do this again. And our second ionization energy is now going to take pretty much, like, think of this as this is what we're going to start off with now. right? That's our new reactant. So now what I have to do is I have to keep going. So I'll make this into a 2 plus. Since they stated the second ionization energy, I want you to think of this has to go to a 2 plus charge, because if we're trying to remove an electron, then that means that we're becoming more positive with our charge, right? Because if you gain an electron, it actually becomes more negative. If you remove an electron, it becomes more positive. So now we're going to a 2 plus, and I just once again add one more electron, because this again would make it the same. So this would have been here. This would have been a positive 1, right? If we add those two together, like 2 minus 1, and then that gives us the correct answer. But this is here, let me erase that. But this is what we would see for the first part. This is your ionization energy of the second half. But in order to do that, you have to figure out the first one first. Okay, so I hope that part makes sense. Let me see what else you had. Effective nuclear charge. Here, effective nuclear charge. I just want my formula of O2 minus. Let me see. All right, here, and I'll erase this part. Okay. Let's see. So effective nuclear charge of something that's neutral versus something that's O2 minus. Sure. I'll start off with the neutral one. So if this is oxygen, what we have to do, it's called Z effective or nuclear charge, effective nuclear charge. So the formula for this would be Z, which is just the number of protons, which we can figure that out using the atomic number of oxygen. So our atomic number of oxygen is 8. Okay, so really that just tells us how many protons there are, or what Z is. So Z is 8, minus the amount of S, which is the average number of electrons between the nucleus. So I'll show you how to figure that out. So this is figuring out what S is. So I would look at the electron configuration of oxygen, which would have been 1s2. Here, let me look at my periodic table. So 1s2, 2s2, and 2p1, 2, 3, 4. Okay. And then now what I would look at is pretty much how many electrons are on the outermost shell. So I would see pretty much how many, yeah, that's what I would look at. I would look at how much are in the outermost shell, which would have been 4 in this case. So I take it from the highest energy, which our highest energy orbital would have been P. Something to also note is if you're looking at that as well, our highest energy typically goes in this order. So S would have been the smallest, P is the next one, D is the next one, F is the largest. So our energy increases as we move down. Okay, so that's just looking at energy, but this is what our S would have been. So Z effective would have actually been 8 minus 4, giving us 4. That's for something that's neutral. Now I have to look at, let's say, something that is not neutral, so 2 minus charge. That means I'm here. So 2 minus charge, that's going to change up our electron configuration. So what Z is still going to stay the same since we still have the same amount of protons. We just changed our electron count. So Z is still going to be 8 because we still just look at the atomic number. That didn't change. But instead, S would be different. So you would typically have, what oxygen would be. However, since this is 2 minus, this instead is going to actually add 2 electrons. And then that's going to fill the p orbital to be 2p6. So now 6 would have been S. So in this case, Z effective would have been 8 minus 6, giving us 2. Okay, that's pretty much it. That's what you would look at. That's the main difference behind it. So I hope that makes more sense how to use everything. But S is really found by doing the electron configuration of that element and then looking at the highest energy orbital. And then however many electrons there are, that's what S is. Okay. All right. And let's see what else. Go back to any others that I skipped. Determine the percent composition of that. And then Esther, for yours, what the percent composition of what exactly? So a lot of times they just ask for like of just carbon, of just hydrogen, of just oxygen. Let me know. For now, I'll just do of carbon, but they do have to specify what element they want you to find the percent composition of. But for now, I'll show you what it would have been. So percent composition is really going to be the grams of the whatever element we're finding here. So the grams of our element, and then the grams of our total compound times 100. So times 100, since it is a percentage. So I would have had to know if it were carbon, oxygen, or hydrogen, or all of them. So let's see. I'm going to start off with carbon. Okay. So if this is asking for the percent composition of carbon of this compound, then I have to figure out how many carbons we have and the entire mass of that. So looking at, we had C2H5COOH. I would look and see how many carbons we have. There's 2, 3. So in this case, I would multiply the molar mass of carbon times 3. And that would have been 36.03. And that's what I'm going to put on top. And then next, I have to divide by the entire mass of the compound that was provided. So let's find that separately. So let's find the entire molar mass of this. I at least already have the three carbons, which was 36.03. Hydrogens, there are 5 and 6 hydrogens. So that's 1.01 times 6. And this is 6.06. And then oxygens, there's 2, so 16 times 2. So that's 32. I would add all of those up. Let's see what that gives us. 36.03 plus 6.06 plus 32. And this is 74.09 grams. So I'm going to put that on the bottom here. 0.09 grams. And then once again, this is just the percent composition of carbon within all of this. So now I'll just divide these two. So 36.03 divided by our molar mass of everything times 100. And then this gives us 48.6% of carbon within this entire compound. Okay, so that's what you would do. Now I'll keep going. Just in case that's what I'm assuming it wanted of everything. So I'll do of hydrogen as well. So now I'll just figure out how many grams of hydrogen we had, which was 6.06, right? That's just in total how many hydrogens there were. And then on the bottom, the entire compound's mass. And then then we can figure that part out. So that would have been 6.06 divided by 4.06. Times 100, which is 8.2% of hydrogen. And then lastly, of oxygen, how many oxygens did we have? We had 2, so a total mass of 32 grams over the entire compound. And multiply that by 100, and that gives us 32 divided by that value again. So 43.2% of oxygen. So that's all you would do. It is knowing the formula. And once again, guys, if you need the formulas, if you want to have one location, one document that has all the different formulas that you need, I can put that link again in the chat. I just got someone say, thank you very much, Melissa, for explaining everything. And so it was name Tom B. Z. Yeah. This would have been, what do you say? For explaining everything in the formula sheet all the way from South Africa. Wow. That's cool. It's awesome to kind of see how many people we can reach through YouTube. So that's awesome. But if you guys need the formula sheet, I'm glad you like that and you're very welcome. I'm really happy that it's helping. If you guys need the formula sheet and want to download that, it's I'll put the chat in the chat. I'll put the link, and it'll help. So this formula was in there as well as a lot of other formulas that you will definitely need. Let's see what else. Okay. We have Hala saying, can you answer this question? I'm struggling a lot. What volume? So it's a titration question. Okay. So what volume? I'm looking for milliliters of H2SO4. And we're given 1.5 molarity of H2SO4. It's required to neutralize 45 milliliters of, this is NaOH, of 0.6 molar solution of NaOH. Okay, and then what I'm going to do first is, because this is a neutralization reaction, I need a balanced equation. So our balanced equation here, let's go ahead and put that up here. But this is an acid plus a base, and this is always going to give us a salt and water. And that's an acid-base neutralization reaction, also known as titrations. So our acid in this case is the one that starts with an H. So H2SO4 plus our base, we know it's a base if it ends in OH. So NaOH, that would then form a salt, which would have been Na with a plus charge and SO4 with a 2- charge. Then this would go, and that would be Na2. So Na2SO4, and then plus water. And then we want to balance this out. So let's balance this out. So here, let me put that to the side. I'm going to put hydrogen, Na, and then SO4. Any sort of polyatomic ion, I want to leave those together, just to make balancing so much easier. And then I'm also going to put that oxygen here. Okay, so this is, we have 3 hydrogens. We have 1 Na, 1 SO4, and 1 oxygen. We have 2 hydrogens, 2 NAs, 1 SO4, and 1 oxygen. And I want to balance out, let's start off with our NAs. So if I put a 2 here, that's really going to distribute to each one of these. So this would have been 2 NAs, 2 oxygens, and I'm going to recount my hydrogens. So we have a total of 4, because 2 and 2 gives us 4. And there's only 1 SO4. And then next, I want to figure out, why don't we balance out our hydrogens and oxygens? So since there's 4 on this side, I need 4 on this side. So I'm going to multiply by 2. So putting a 2, I will have 4 now. And then how many oxygens do we have? We have 2. Everything else is now balanced. Cool. So that's what we would want to do first. Always start off with your balanced equation. So now that we have that, I can proceed with this question. Okay, let's just make this a tiny bit neater. There we go. Okay. So now that that's balanced out, what we're going to do with this type of question is, because we're looking for milliliters of H2SO4, I actually want to start with the one that we're not looking for. So we're looking for H2SO4. I'm going to start off with NaOH. It's just how it's going to work. Okay. So I would do milliliters of NaOH. And then our next thing would be going from milliliters to liters of NaOH. Using the molarity that they gave us, we would be able to get to moles of NaOH. Then do a mole to mole ratio to get to moles of H2SO4. And then next, using the molarity that they provided of H2SO4, we would have gotten liters of sulfuric acid, or H2SO4. And lastly, convert it to milliliters of H2SO4. Okay, that's exactly what I'm going to do here. And then just a little side note, looking back at our molarities, how we can rewrite these as conversion factors is just moles over liters. So this is really going to be 0.6 moles divided by 1 liter. Same thing goes for this one. This is really 1.5 moles over 1 liter. So I'm going to use those in just a second. So let's start off with the 45 milliliters and change that to liters. So 45 milliliters of NaOH, I would multiply this by 1 liter on top and 1,000 on the bottom, because those would cancel out our milliliters and milliliters. And now we have just liters of NaOH. Now I'm going to keep going and now multiply by the molarity that was provided. So our molarity that was given was this 0.60 moles of NaOH and 1 liter of NaOH on the bottom. So our liters and liters would cancel. We're now at moles of NaOH. And now I'm going to multiply by my mole to mole ratio. So moles of NaOH would be on the bottom. Moles of what we're looking for, which is H2SO4, would be on top. Where I'm going to take this mole to mole ratio is using the balanced equation that we just found. So in this case, we have 1 mole of H2SO4 per every 2 moles of NaOH. So that's what I'm going to put here. So 1 mole per every 2. Okay. And then I'm going to keep going. And moles of NaOH would cancel. And I would multiply this by, let's see. Next, I need the molarity of H2SO4 that was also given. So on the bottom, I'm going to put moles of H2SO4 so they can cancel, which would have been 1.5, and 1 liter of H2SO4. Last step, since our moles and moles cancel, is to just convert this liter to milliliters. So on the bottom, I'll put 1 liter. On top would be 1,000 milliliters. And this is H2SO4, H2SO4. And now we have to multiply everything out. So you'll note that you could actually get rid of those 1,000 since they're really being divided, so I can cancel those out. And then now what I'm going to do is just multiply 45 times 0.6 and divide that by 2 times 1.5. So let's see what that gives us. So 45 times 0.6 divided by 3, really. So that gives us 9 milliliters of H2SO4. All right, so that's what we would get for this type of question. I'm going to see if I can put, I don't know if you can see it already, but I really put a different video on molarity and solution stoichiometry. I can put that back in the chat. And then I also have molarity notes that I've created. It's a how-to guide on how to figure out pretty much solution stoichiometry. I put every single possible way that I can think of them asking the question, as well as how to use molarity as a conversion factor, how to find it, and all the different ways that I can possibly think of that they can ask on your exam. Okay, so I'll see if I can put those in the chat right now. I'll put the videos that are going to help you, as well as the notes that I highly recommend. Okay, so let's see what's next. Okay, so I have another question. All right, let's see. Wait a second. All right, so I have our next question here. It's from Tom BZ Zoo. So we have aluminum and HCl acid, and we're given our balance equation. Cool. So we're given our balance equation. Let's see what this question is asking. Okay. So we're given 355 milliliters of H2 are collected over water, yes. So we're given our volume, we're given our temperature, 299 Kelvin, and an atmospheric pressure of 0.9930 atmospheres, and find the mass of aluminum. And then let me just make sure. So everything for our volume was for H2. Got it. And then we're looking for a completely different one. And then our vapor pressure, that's what we were missing. So our vapor pressure was 0.03320 atmospheres. All right. This is a collected over water question where there's a specific, kind of like that keyword collected over water should clue you in that you have to subtract the atmospheric pressure from your vapor pressure. So to figure out what the actual pressure of your gas is, which in this case is H2 or whatever you're solving for, but in this case it's H2, I would take the atmospheric pressure and subtract that by the vapor pressure. This is always going to be the case whenever they tell you it's collected over water. Okay, so make sure to note that. Collected over water, boom, instantly know I have to subtract those. So that's exactly what I'm going to start off with. So this is going to give us the pressure of H2. Our atmospheric pressure was at 0.9930 atmospheres, and then they gave us our vapor pressure. And then we'll go from there. So I'll subtract those and see what that gives us. So let's see, 0.993 minus 0.0332. This gives us 0.9598 atmospheres. So that's what I'm really going to use. Now, the next step with this is because they give us everything in according to H2, and we want to find the mass of aluminum, well, first we have to figure out how many moles of H2 we have, and we'll use the ideal gas law for that. So that's actually the first step, or the second step in this case. Our first step was just to get the correct amount of pressure that we have. Our next step is to use PV equals nRT and solve for N. So I'm going to rearrange this formula by dividing RT to both sides. And then RT cancel. N is now equal to PV divided by RT. And then I'm going to plug everything in, and this is going to give us the moles of H2. And then we'll get to the moles of what we're solving for, which is aluminum. So N is equal to our new pressure that we found. So this value, 0.9598 atmospheres. Our volume was not in the correct unit. So let me go back and change that to liters. So we have milliliters. I want that to be in liters. So all I have to do is divide by 1,000. And this is going to move over the decimal place 1, 2, 3. So this gives us 0.355 liters of H2. And then here, let's plug that back in. So this is 0.355 liters. And then on the bottom would be our R, our gas constant, which is 0.0821 liters atmospheres divided by moles Kelvin. And then that's why I wanted it in liters, because our gas constant is in liters. So you want all of your units to be pretty much according to that gas constant, so everything can cancel to give you what you're solving for. So now our temperature would have been 299 Kelvin. Your Kelvin cancel, liters cancel, and atmospheres cancel, and we're going to be left with moles. So, and specifically the moles of hydrogen, of H2. So let's figure out what this gives us. So I'm just going to multiply the top first, and then divide by the bottom multiplied. Let's see what that is. That gives us 0.014 moles of H2. So then now what I'm going to do is, using the balanced equation that they gave us, we have to figure out how many moles of aluminum there are. So we have the moles of H2. We're going to do a mole to mole ratio. Moles of H2 would go on the bottom, and on top would be moles of aluminum. All right, so then now I'm going to go back to our balanced equation, which was up here. And we'll see that there's 2 moles of aluminum per every 3 moles of H2. So that's what I'm going to use. So I said 2 moles of aluminum per 3 moles of H2, and let's figure out what that would be. So 2 times 0.014 divided by 3. That would give us 0.009 moles of aluminum. Last step is to convert this to grams. So let's do that. So then we'll look at the molar mass of aluminum on our periodic table as this processes. So all I have to do is multiply, because they want us to figure out, they said find the mass of in grams of aluminum. So from this step, from our moles, I just have to find the molar mass of aluminum and multiply by that. So give this a second to process. I know I have a lot on the screen, but pretty much right after this step, we're just going to multiply by the molar mass of it. I'm hoping that this is, there we go. So I multiply by the molar mass of aluminum, which was 26.98 grams of aluminum and 1 mole on the bottom of aluminum. Okay, so we'll multiply those two values together, and let's see what that gives us. That gives us 0.25 grams of aluminum, and let's just double check our sig figs. So sig figs, I'm actually going to add a couple more, so this would have been 1/8. They want 3 sig figs, so I'll round up. So this really gives us 0.252 grams of aluminum. And that would be our final answer for that. Okay. Let's see. And I'm seeing, okay. So next question, let's go back to Hala. And she says, thank you so much. I was just confused because my teacher, instead of using solution stoichiometry to answer the question, used the equation of, got it. They used the dilution. I see. That wasn't necessary to use, yeah, because they weren't diluting, but you're welcome. How would you solve my previous question through that means? Is it the same process? Let me look at it again. So, oh, I see. To neutralize the reaction, what volume of that is required? You know, it's not possible. That's why I'm actually shocked that he would have done it that way, because that's not the correct way to do it. With dilution questions, they have to be the exact same like acid or solution. So like here, I'll explain what we use. C is going to stand for concentration, or really molarity. You could have seen it this way with C just meaning concentration, or you could have seen it as molarity. So there's two different formulas. They mean the exact same thing, where C and M are exactly the same thing. Now, you can see if it would have given you the same answer. However, that's not typically what you would do for these types of questions. And actually, yeah, not even. I'm actually shocked that he even did that, because it wouldn't be correct. But what you would do would be, and we can check if it actually gives us the same answer since it tells us to neutralize it, but C1 would have been 1.5 for our molarity of H2SO4. And then, let's see, then C2 was the other concentration that they gave us, which was 0.60 of NaOH. And right then and there, that's why it's off, is because both of these should be the exact same. But we'll keep going. And then our V1 is what we're solving for. And then V2 was the 45 milliliters. And you would plug everything in. So what I'm assuming, was doing was just multiplying these two together. We don't know what V1 is. And then C2 was 0.60 times 45. So let's see if that, I hope I remember the answer. I think I do. Yeah, no, it wouldn't work. So I believe your answer was a lot larger, but it wasn't 18. I definitely remember that. And then this is not correct regardless. Like, you wouldn't do it this way. And the reason for that is because you definitely need these exact, these to be the exact same. So I don't know why he's using dilution formula. That's not right. This is like how we did this in the beginning was correct. Okay, that would have been solution stoichiometry. Yeah. So let's see another person's question. Okay. So Rita asks, could you help me figure out the pH, pOH, and concentration of acid, concentration of base for this? So sure. We are given our concentration of an acid, and it's telling us hydrobromic acid, which I'll translate for you guys. This is a good little review on naming acids. So the hydro tells us there's no oxygen. The acid part tells us there's an H plus in front, and this is bromic, or really bromine. So this is HBr. This is something to also note. The fact that this is actually one of our strong acids tells us that if the concentration is given of a strong acid, then that equals the concentration of H plus. Okay, so in this case, since I know that yes, HBr is a strong acid, and I can put some of the common strong acids that you would see. The common ones are HCl, HI, HBr, HNO3, and I believe there's several others, but those are the most common ones that I personally see. But those are some of your strong acids, so that's how I knew that yes, this is going to be the exact same concentration of hydronium or H+. Okay, any single time I say like hydronium, I mean this. This is hydronium, okay? And that's really just saying the acid concentration. So this is answering the first part, right? That I know is the acid concentration. Now we can figure out the pH by using another formula. So our pH is equal to negative log of our acid concentration. So all I have to do is plug in this value into my calculator and figure out what the pH would be. So negative log of 0.035. This would give us 1.46, and that's our pH. It's very acidic. Makes sense because it's a strong acid. Then now I can figure out what the pOH is by using this next new formula. So pH plus pOH is equal to 14. And once again, I'm just going to plug in what I know. So 1.46 plus pOH is equal to 14. And then I'm just going to subtract this over. So I'll subtract over 1.46 minus 1.46. That cancels. We get pOH, and let's see what that is. So 14 minus 1.46 gives us 12.54, and that's our pOH. Now to figure out our concentration of OH, this is going to be 10 raised to the negative pOH. So I'll just plug in that value that we just found. So I'll substitute that in here. And this is really now going to be 10 to the negative 12.54. And that's going to give us our concentration of our base. So let's see what that is. So I would do second log on my calculator and then negative 12.54. Put that in parentheses. And then this gives us a concentration of 2.88 times 10 to the negative 13th. And this is molarity since it is a concentration. So that's what you would use. And I think something to kind of like note, these are some of the formulas that you would see, like pH is equal to negative log of our H plus, pOH is equal to negative log of OH minus, pH plus pOH is equal to 14. These are just formulas that are going to be helpful to you. OH minus is equal to 10 to the negative pOH, and the last formula is H plus is equal to 10 to the negative pH. And you would use that formula in the case that they gave you your pH and asked you to work your way backwards and figure out the concentration of H plus. Okay, so that is pretty much everything for pH that I can possibly see them throw in this type of class. We do have some more time. So if you guys have more questions, by all means, ask them. I will answer them. This time is for you guys. So let me know in the chat if you guys have any more questions and you want me to clarify anything else. I see a lot of thank yous, and I'm happy you guys are appreciative. I'm appreciative of that as well. I see Lizette saying thank you for the clarity. And then same with Hala saying thank you. You're welcome, guys. Really, I'm so happy that it makes so much more sense now. And then Rita saying thank you so much. You're welcome. Very welcome. I love that it actually makes sense. It's such a beautiful feeling to have something that once was so complicated now seem like really that was it. You know, I love that feeling, and I love seeing that in my students as well. So if you guys have any more questions, please let me know. I can see what other types of questions I can come up with, but I'll wait for you guys in the chat to ask more questions. As I mentioned, we have like a little less than 20 minutes, so that's plenty of time for me to keep answering questions. Let me erase all this and let's see what else you guys ask for. So Breck is saying nuclear chemistry. Sure. So I can pull up a couple of my nuclear chemistry things here. Hold on. Sure. So we can go over the different types of decays. Like, let's say we can start off with alpha decay and beta decay and understanding what everything really is. So let me pull up my example with this here. Let's say I want to get an example. There we go. Okay. So let's say if we were asked to do alpha decay. Okay. And alpha decay, the symbol for this is either going to be a helium atom, which is the most common one, or it's going to actually have an alpha symbol. And this is going to be 4 and 2 again. Okay. Yeah, got it. Alpha, beta, and gamma. Perfect. Okay, yeah, I'll do that. Thank you for specifying. So if we were to do alpha decay, and let's say if they ask us to do alpha decay they would ask it this way. They'd say, find, or actually not even, they would say write here. They'd say write the reaction or equation of alpha decay. So let's state, and this is processing, sorry. Let that load for a second, and then I'll answer. I'll do alpha, beta, gamma, and then I'll also do Esther's question as well. So main thing as this loads, main thing with alpha decay, how it's going to pretty much be different from everything else is that your atomic number and your mass number are both going to change, okay? So both of those are going to change. And then with beta, only the atomic number is going to change rather than the mass number. So I'll show you that. Now, real quick, guys, when you're doing alpha and beta decay, this goes back to remembering which one is which, okay? So what is the atomic number and what's the mass number? Well, A is actually going to refer to the mass number, all right? And Z is going to refer to the atomic number. I wish that they put that A was, so it would be more obvious, but they didn't do that, unfortunately. But Z actually means atomic number and A actually means mass number. Okay, so what I'm going to do is I'm going to do the alpha decay of, let's say, PO, and we're given that 210 or whatever number they're giving you, that's going to be the mass number. Okay, so they're always going to give you the mass number. However, you would look on your periodic table and find the atomic number. Okay. Then in this case, PO, I would put PO and 210 on top, and then the mass number, actually the atomic number of PO found on the periodic table would have been 84. And then what's going to happen with these types of decays is you're going to start off with just a larger atom or element, and that's going to decay or break apart. And then that's why I'm putting helium here now. And then plus, to figure out what its new element that it's going to be, is you would subtract. So I'm going to subtract both of these now. So I would subtract the mass number -4 and the atomic number -2. So then this would give us a new mass number of 206, and then 82 would be our atomic number, and that's how you figure out what element that is. Because it tells you, oh, the atomic number is 82, you look on your periodic table, and that would tell you that it's lead or Pb. And then that's how you would figure out what alpha decay is. Let's say if you had to go backwards, okay, and you didn't know what you started with initially. Well, they would have to give you lead and tell you that it's alpha decay, and you would just add these together to give you that 210. So that's kind of something to look at. Anything that's on the same side, you add together. Anything on opposite sides, like the reactant and the product, you subtract. So that would have been alpha decay. Once again, alpha decay is the only one where your mass number and your atomic number will change. For beta, only your atomic number is going to change, not the mass number. So in this case, for beta decay, what you would see is an electron, 0, -1, that would be the symbol, or then our other symbol would have been beta, okay? The typical one would have been an electron, that's what I typically always see, but they could also state beta, and then once again, we'll do the same sort of process. So you would start off, and then turn have that be, what was it, 131. That would give you the mass number. And once again, I'm going to kind of set this up, and this would have been 131. And then our atomic number of this would have been 53. This is going to break apart, and I would put an electron. And then once again, I'm going to subtract. So nothing's going to happen with our mass number. So that's just 131. And here I'm subtracting, but really I'm going to add because both of these negatives would cancel to turn into a positive. So we would have 54, and then looking at our mass number, or our atomic number, I'm sorry, that would then tell us the element is xenon. So that's what you would look at for beta. For gamma, there's going to be really no change. So here, if we were to have gamma, let me show you the symbol for gamma, and here's an example. So here's gamma. All that's happening is it's going from, like, the element or whatever you have is going from an excited state. So let's say cobalt, and I would put some sort of star, little asterisk, just representing that it's in its excited state. And this would have been, once again, the mass number and the atomic number. And then the symbol for gamma is this kind of funky looking Y, and there's a 0 and 0 on top. There's the only change that's happening, like there's no change in your atomic number or your mass number. Essentially what's happening is it's just going from an excited state to ground state. So excited, think of it as it's reactive, okay? And ground state, it's no longer as reactive. So that's essentially all that's happening with gamma. All right, hope that makes some more sense. And let's see, I can answer another question. But that was nuclear chemistry. That was alpha, beta, and gamma radiation or decay. And then I'll answer Esther's question. Okay. So answering Esther's question, oxygen gas occupies a volume. So we have a volume of 185 milliliters at a temperature of 26 degrees Celsius and has a mass of 0.47 grams. What's the pressure? Okay, so we're looking at what the pressure of our gas would be, and the fact that they tell us that it's oxygen gas. I know that that's just O2 because any single time we have anything that's diatomic, and the diatomic atoms, by the way, I like to think of this as John. That's just how I've always remembered it. But that would have been carbon, and how it's going to exist as a gas just means it's in pairs, okay? So it's like diatomic. Same goes with our halogens. Those are going to exist. If it's a gas, it's going to be diatomic as well, and so on, okay? Like I2 and so on. So O2 would have been what we have here. So what I have to do, since I want to use PV equals nRT, or the ideal gas law, then I need the amount of moles. I'm going to change the mass and convert that to moles. So all I need, O2, this would have been 16 times 2, since there's 2 oxygens. So it gives us 32. So I'm going to put 32 grams of O2 on the bottom per 1 mole of O2 on top. And then this is going to be 0.47 divided by 32. And that's 0.0147 moles of O2. Okay. So the next thing is we want to make sure that everything's in the correct unit, which we don't have that right now. We just changed the moles. Let's change our temperature to Kelvin by adding 273 Kelvin, and then this is really going to give us Kelvin. So 273 plus 26 gives us 299 Kelvin. I'm also going to change the volume to liters by dividing by 1,000 on the bottom, and this will give us 1 liter. Really, I'm just moving the decimal place over 1, 2, 3 to the left, so that would have been the correct unit. Now I'll plug everything in and find our pressure. So using PV equals nRT, and then I want to solve for P, so I'm going to divide by the volume, so then it just makes it easier to just plug everything in and solve. So then now I just have P equals nRT divided by V. So our N was the moles that we just found, which was 0.0147 moles. And then R would have been our gas constant. So that's 0.0821 liters, atmospheres, moles, and Kelvin on the bottom. and then times the temperature in Kelvin. For any sort of gas law, we always want our temperature in Kelvin. This is 299 Kelvin. And then on the bottom, we have our volume changed to liters. And what would happen is that your moles and moles cancel. Kelvin and Kelvin cancel, liters and liters cancel, and you're left with atmospheres. That's why you want all of your units to be like the specific unit of our gas constant. Okay, so now I'm going to multiply everything on top and divide. So let's see what that gives us. 0.0147 times 299 times 0.0821 and divide by 0.185. So this would have given us 1.95 atmospheres. I'm going to double check that that's the correct amount of sig figs. We were given, yes, that would have been the correct amount since our least amount of sig figs is really 3. So that's it. That would have been our atmospheres. Let me see if I can answer another question from April. Okay. So April says, hi, Melissa. If you added 50 milliliters of water, so we have 50 milliliters of H2O, to dissolve the oxalic acid dihydrate instead of 30 mils, would that require more or less or the same amount of NaOH solution to titrate? Explain. So let me see what that acid would have been. So oxalic acid dihydrate. Here. Let me see what that formula would have given us. So that would have been CHOH. Actually, hold on, because that's vital for this part. So oxalic acid dihydrate would have been C2H6O6. And then we have water. What's the other part of the question? Let me see. So if we added 50 mils of water to dissolve that instead of 30, would that require more or less or the same amount of NaOH solution to titrate? I see. So if we added more, because you're pretty much diluting this. I see. Oh, times 2. Yeah, that's fine. So they actually give you it, April. I see. Okay. That's fine. Thank you. 4 times H2O. Yeah, and it actually is the same thing, just to let you know, because this would have been 4 hydrogens and 2. That's why I put 6. And then same thing goes here. There would have been 2 oxygens and 4 and giving us 6. But that's another way to write it. No problem. We actually don't even need a balanced equation. Instead, what you can look at is the fact, this is what I want you to think of with titrations. This is more of a conceptual question where if we were to have, let's say, some sort of solution, okay, and then in the solution, that's our actual acid. Okay, so H2, 2O4, that's the oxalic acid. Now, if we were to dilute this, meaning pretty much put a little bit less water in this case, so if actually, no, a little bit more water in this case. So if we added 50 milliliters of water, what's going to happen is it's going to weaken that acid. So if we weaken that amount of acid, like think about it this way, where if you had orange juice, okay, and it's typically really, really concentrated. So maybe if you took a sip of the orange juice, it's way too sweet. So if you added 50 milliliters of water, it's going to be really watery now, right? It's not going to be as sweet, and that's like diluting it. That's the same concept with this acid. So if we added a lot more water, that's going to weaken the acidity of that acid. So what's going to then happen is we're going to require less base to neutralize it. But if we added, let's say instead, if we had 30 mils of water, which is a lower amount of water, then that acid wouldn't be as weak compared to adding 50 milliliters of it. So then it would have required more. So if we add, so like the question here is, would we require more or less or the same amount of NaOH? We would require less. So, and it's just because by adding 50 milliliters of water to that acid, you are weakening that acid. It's no longer as acidic, and then therefore it will not require as much NaOH solution. If I wanted to get even more technical, I could. And actually, I think that's actually totally fine. I don't expect you to talk about like the intermolecular forces and whatnot. It's really just going into, it weakens the amount of pH or acid, really. The acid concentration goes down. That's what you want to talk about. So I would state that your concentration of your acid decreases. Okay. Therefore, your concentration of NaOH would also decrease because it's a weaker, because it's now a weaker acid. So I hope that makes some more sense. And I have AA saying, my stoichiometry project is due today at 11:59 and I haven't started. Why haven't you started? I would say start. If you need help with stoichiometry, I do have a playlist that I can put in the chat right now. But yeah, definitely check that out. Last question from Donna. Can you clarify how to determine the hybridization of a central atom? Absolutely. So what you're looking for with hybridization, you're focused on the electron geometry of that central atom. So like, let's say if you were to have something like, and I'm just going to actually put a bunch of these just to help you understand. Here, that's tetrahedral. This would have been, oh, let me not put that. Let's put boron. Yeah. Trigonal planar. We'll do something linear and so on. Okay. So I'm going to look at all the different central atoms here and figure out what the hybridization would have been. So in this case, our central atom would have been carbon. If our electron geometry is linear, then it's going to be a hybridization of sp. All right, and that's always the case. It's always going to go hand in hand with electron geometry. And what I'm looking at really is how many bonds or electron groups are on that central atom. So here it would have been 2, really, that's why it's linear, so sp. I'm going to keep going. Trigonal planar would have been our next one. Okay, trigonal planar. And then this would have been 3, so because there's 1, 2, 3 bonds attached to that central atom of boron. So now this is sp2. And then this keeps going. So now for 4, right, 1, 2, 3, 4, this is now tetrahedral. That's why it would have been sp3. And so on. If it were 5, let's say, I have to think about that one, that would have been p, 1, 2, 3, let's say a bunch of fluorines. Okay. Sure. This would have been trigonal bipyramidal. Trigonal bipyramidal. And then that's going to be sp3d. And lastly, octahedral is the last one. So that's 6. Let's say if there was 6 fluorines now. And I mentioned that would have been octahedral. Then that would have been sp3d2. And that's actually the entire hybridization chart list. So you're really just looking at what's the electron geometry of that central atom, and then it tells you, right? If it's linear, sp, trigonal planar, sp2, and so on. So I hope that makes some more sense, but this is really the main part of it. And then I want to say, I do, cool. So on the formula sheet, I actually do have hybridization. I even have electron geometry and molecular geometry. So if you guys haven't downloaded your free chemistry survival guide, which is just all the formulas and anything that I personally felt that I wish I had all in one document, I put it all together for you guys. So make sure to check that out and download that. It's definitely going to help you with your exams coming up. But yeah, Donna, that would have been it for this question. Hybridization is also found on our formula sheet, and I have that all nicely laid out. Okay. All right, guys, that is going to be it for today. Thank you so much for joining me, and thank you so much for appreciating these Q&As. That truly means a lot. I enjoy helping you guys out, and I enjoy teaching overall. It's my favorite thing to do. So I will be doing, this is actually the end of the 2-hour sessions that we're doing. Okay. Instead, what we're going to be doing is I'm still going to be meeting on Sundays, still doing my typical times from 12 to 1. So if you still have your final coming up and you still have time, I will be doing this again on the next Sunday, just for an hour though, from 12 to 1. So bring your questions. I hope to see you then, and have an awesome Sunday and Memorial weekend. All right. See you guys.